It is section 2.5, solving linear systems by metric factorizations. In industrial and business applications, the linear system is often sparse. This means that number of non-zero entries is small. The number of zeros is larger than the number of non-zero entries. And the system must be solved for multiple right-siders, for different right-siders and inputs. The system must be solved again. For these common problems, the LU factorization is very useful. You may try to use the inverse technique. The inverse of a metric usually becomes a full metric. Of course, when you apply LU factorization, number of non-zero entries will increase, however, is not so much. So it is much more effective. Here we have a metric A, an n by n metric, and the LU factorization of A is defined in this way: L and U product. L is a unit lower triangular metric. That means that along diagonal the value is 1, and only non-zero appears in lower portion, and is a square metric. And U has the same size as the metric A, and U is on echelon form of A, and so that it is upper triangular matrix, like this. This one is upper triangular matrix, and lower portion strictly below the main diagonal, the entries must be 0. Okay. Here, let's assume we have to solve this linear system. Then, once it is LU factorized, then we can write in this way. For UX, if we write this one as Y, that is Y, then it introduces this solver, Ly equals B, and then to find x, you have to solve ux equal y. So by using these two-stage solve, and you can get the solution x. But each algebraic equation can be solved very efficiently using substitutions. Now, to get an LU factorization, we'll try to use elementary row operations. Every elementary row operation can be expressed as a metric to be multiplied from left-hand side. And such a metric is called an elementary metric. And every elementary metric is invertible because every elementary row operation is invertible. And for instance, replacement, and Ri is replaced by here Ri plus some constant multiple of another row, Rj. Now, inverse of that operation is just subtraction. And k times added, and once k times is subtracted, then it will go back to original 1. So it is invertible. And interchange, Ri, Rj, interchange, row change, and if you try to change it once more, then it will become the original 1. Also, scaling, you multiply some constant k, which is non-zero for one row. That is scaling, but its inverse is just divided by k. So every row operation is invertible. That's the reason every elementary metric is invertible. Okay. Okay. A is given as in this metric. Reduce A to an echelon metric using replacement operations. In algebra factorization, major operation is the replacement operation. And express the replace operations as elementary matrices and find their inverse. Okay. Now from A here, we will try to reduce it to an echelon form. Now here, one is pivot, and from this one, okay, we now try to subtract twice our first row to get that one 0. So the first row is 1 minus 2 and 1, and second row will become, yeah, that is 0. Twice subtracted, that will make here now 2, because 4 must be added. Twice subtracted, then it will become 1. So here, first operation is now R. 2 is replaced by R2 minus twice of R1, right? And now you may also eliminate this one. And okay, but we'll do it step by step. Okay, minus 3 and 2 and 0. Okay, for that one, we write here one more here. Okay, we eliminate this one. So 1 minus 2 and 1, 0, 2, 1. Okay. Now here 3 times added equals 0. 3 times added, so that minus 4. 3 times added, so it is 3. Right? Okay. So that is same as R3 is replaced by R3 plus 3 times R1. Right? Okay. Now to reach at the echelon form, here we have to apply one more time. Now here, this is the pivot, and twice added, then 1 minus 2 and 1, 0, 2, 1, and then twice added, then it's 0, twice added, then it will be 5. Okay, here, R3 is replaced by R3 plus twice of R2. Right? Okay. Now, for each replacement, we'll try to get the corresponding elementary matrix. For this one, now, okay, elementary matrix can be made in this way. Start from identity. Okay, we put here now identity. And for that one, this will be multiplied. Okay, if we say this one is now express the matrix E1 to be multiplied left hand side, then we change some value here and multiply 1 minus 2 and 1 to A, 2 minus 2, 3, and minus 3, 2 and 0. Then this one must be 1 minus 2 and 1, and then 0, 2, 1, and minus 3, 2, 0, right? So we have to change it a little bit here now. But in this matrix multiplication, we do row column operation. So here, the second row is changed, and in fact, minus 2 of R1 is applied, so that you have to change only this row. And second row, because the output, related output is only that one. Now, you have to put something. We have to change this one. How about this one? That position, we put minus 2. Okay, minus 2. Then, row column. So that minus 2 will be multiplied to first the row here, and also first row here, and first row here. So that if you put here minus 2 for that position, then this one will make minus 2 times of that first row will be added to that one. That is exactly this replacement operation. So this matrix is the corresponding elementary matrix E1. Okay, so in this way you can find it. But if you do several times of practice, then you can easily see that okay, this minus 2 will be here in now 2, 1 position, R2 and R1, so that 2, 1 position minus 2. You can put it. Now, by using the observation, okay, that is now 3 on position 3 from identity matrix. Let's check it. Now, that is 1, 0, 0 and 0, 1, 0. 3 on position, we have put 3 and 0 and 1 from identity, and then it is applied for that matrix, so that we put here 1, minus 2 and 1 and 0, 2, 1, and then there is a minus 3, 2, 0. Then the result must be same as that. Okay, let's check it. There is this row column. Okay, the first row is not changing. There is 1, minus 2 and 1. The same way, row column. Okay, it's not changing. Now for the third row column, 3 times of this one will be added, so it is 0. 3 times added, so it is a minus 4. 3 times added to 0, which is 3. So exactly we have that. So in this way, you can find the elementary the matrix for the elementary row operations. Now we can see easily, okay, that one is now at 32 position, we put 2, right? Okay, so here start with identity matrix. And now 32 position is this one. There's 2 and 1. And we put here extra component. Here again, extra component for the identity. Then again, now we put here the result here. Then you can easily check that this is exactly the corresponding elementary matrix. Okay. Now, and here we have to consider inverse of each one. That is R2 and is replaced by here R2 minus 2R1. Its inverse must be here change the sign only. Then it'll go back to original 1. For that one, if you apply now here in rather than minus 2 and along with plus 2 apply this one, then you'll get the original 1. So that is exactly the inverse. You can easily check that. So eventually, if you change the extra non-zero and the sign of those entries, then the result will be inverse of elementary matrices. So if you change this one with 2, then that is its inverse. You change this one by minus 3, then inverse. Okay, minus 2, then it's inverse. Quite simple. Okay. Okay, here the LU factorization algorithm is organized in this way. This derivation introduces an LU factorization. Okay, A is an m by m matrix. Then first we put m by m square identity matrix in front of A. So this multiplication is the same as A. Now we apply E1 first elementary row operation. And in fact, there's the replacement operation and its inverse, so that these two will be cancelled out to become A. Once applied, then we multiply its inverse here. The same way between over there, after eliminating one entry below the pivot, and we can eliminate another one by applying E2, then E2 inverse must be given. You can see here blue color. The blue, the matrices will become later L matrix. And now, if you do this operation again, so reach at an echelon form, then, okay, that is echelon form. Then here, exactly the same way, elementary operation, elementary metric is inverse. Elementary metric is inverse. So that this is now echelon form, then it's U, and this portion will be L. Here, EI, each EI is the elementary metric for the replacement operation, then it is true. Okay, so here we summarize the algorithm. The LU factorization algorithm without pivoting. The pivoting means row change. Row interchange is not applied. In many applications it's possible, but later on, and in the later part of the section, we'll see pivoting and so-called partial pivoting. But here we'll work on LU factorization without change of rows. Okay, uses a sequence of replacement row operations to get from A. We are multiplying E1, E2 up to EP, and a sequence of replacement to get echelon form. Then it will become U metric. And now left hand side here is from identity that is applied. So that basically during the computation, and from right side, E1 inverse is multiplied, E2 inverse is multiplied, E3 inverse is multiplied, so up to EP inverse is multiplied from right side. Then each the elementary metric for replacement is lower triangular metric, so their multiplication will be lower triangular metric. Here we see here earlier in this example, now these are elementary matrices, and their inverse is also elementary matrices. And if you try to multiply lower triangular matrices, then again it will become lower triangular matrices. Okay. So that will become L. That's the idea of LU factorization. Let's see here LU factorization of this metric. Okay. Now, with pivoting, this is a kind of reaching at U, which is echelon form. So when you try to get reduced to echelon form and reaching at on echelon form is for the phase of elimination, and also this is called Gauss elimination. Okay, here this is a pivot, and 30 times must be subtracted. Okay, that's the first operation to make this one 0, and now twice is added like that, so it is a second operation, and now to eliminate this one. Now here the pivot is moved from here to there, and now for this one, okay, 3 over 4 times of R2 must be subtracted to make it 0. So that is exactly this one, and that is E3. You can get also the elementary matrices for these three quite easily, and the inverse also we did earlier in the previous example. Okay, so we reach at on echelon form, that is U. Now we collect here the replacement row operations and their inverses. Now, from A to U, from here to there, we applied that operation, and then this operation here, the coefficients over there, minus 3 plus 2, and then now that one, minus 3 over 4 here. Okay, we applied in this way. In metric form, we can write in this way: A, E1, E2, E3 are multiplied from the left-hand side to make U. So A can be written here in this way. So that will be now L. So in fact, L is from right side is multiplied E1 inverse, E2 inverse, E3 inverse multiplied. Okay, so that here now, here from I to L, we consider in this way E1 inverse is just change the sign, that is applied, and now from right side, so be careful here. Now arrow is the other direction because it's multiplied from the right side. Okay, now E2 inverse and E3 inverse multiplied. Now let's try to construct the metric L. L is originally here identity times here right multiplications, but for convenience we may eliminate the identity, and also we may put the identity on the right side. Either way is okay, because identity is not changing anything. If we put identity to the right side, then looks like here, the first we apply E3 inverse, and then E2 inverse, and E1 inverse. Okay, let's do that. Identity, E1 inverse is this one here, and E3 inverse is this one. Change the sign, so that plus 3 over 4. Second row, 3 over 4 times second row is added to third row. Okay, we multiply 3 over 4 here and add here, so exactly that one, right? And after that, and E2 inverse, okay, that is E2 inverse, and R3 third row is now replaced by third row times minus 2 R1. Okay, so here minus 2 times R1 is added, so it becomes minus 2. And E1 inverse, first row, 3 times third row is added to second row. Third row, 3 times this one is added here, so it becomes 3. So that is now L is constructed. Okay, so in this way you can construct L. It is a unit lower triangular metric. So let's consider a little bit more for that one. The metric L simply collects all the constants of inverse, the constants of inverse replacements. Here, that is 3 minus 2, and that, yeah, here 3 minus 2 and 3 over 4, which are the same as ratio to pivot values. Okay, that means that here for this pivot, we can measure the ratio. There's 3 and minus 2, 9 over 3 minus 6 over 3. That is now 3 and minus 2. For that pivot, the ratio is 3 over 4. That is exactly this one. Okay? So it looks like it's collecting the ratio to the pivot, then that is eventually the L metric. Okay, so that is the main observation from this computation, and in practice, the L factorization is implemented in this way. Okay, the same problem. Now start with A here. Now first here, now 3 is the pivot, ratio, and put over there. And we try to overwrite ln u, because in over the LU factorization, it is empty. It is empty now, and that one is, but we are using this information later on. But now we try to save this information here along with its negation, right? That's exactly this one. That is ratios, and then the negative of the ratio is operated for this portion. You don't have to touch this one. In U metric is 0, so you don't have to touch. Only this portion is now changed. So the 3 times of first one is now subtracted there, so become 4, and 3 times, so the minus 1. Now for this row, and negation of that one is 2, twice of this first row is added, become 3, twice of this one now, that is minus 3. So we done this one, and of course here now, L portion is saved. One more time, now it becomes pivot. Now the ratio is 3 over 4, we save here, and then minus 3 over 4 times R2 is added to R3, so that from here, and that, then we can get that one. So that's the final result of LU factorization. From this one, still lower portion represent the L metric. We copy this one here, and the diagonal is 1, and upper triangular, including the diagonal, will become upper the U metric. So that out of this one we can get it, and so and we can overwrite the LU factorization in the same position, in the same memory, so that we can save storage requirement. Okay. The LU factorization algorithm, when it is working without pivoting, then it can be implemented quite simply, like that one. LU no pivot override. For given A, we measure the size, and then here, once pivot, kth pivot, then and the below of the pivot, and the values are divided by the pivot value, so it is exact ratio. And then for ratio, now there is moving, J is moving from K plus 1 to M. Now, okay, so that maybe we may try to use I notation. But anyway, here, so then moving over, J is moving over there for each row. Now here, along with the negation of the ratio, once it is divided by that one, then minus this quantity will be negative of the ratio, and the kth row will be subtracted, and we get that. Quite simple. In this way, we can compute the metric. Okay, for, let's see how it is working. Okay, here we have this one. Now I put here the same metric and call this LU pivot override A. Okay, let's see that one. That is this one I implemented here, and we run this one calling the function, and function 5, F5 is execution key. Then you can see the output in command window here. That is the output, and you can compare with this output, and in here okay, that one is exactly same. Okay, let's see that one. Okay, this one and that one are the same. Okay. Okay. Here, try to find the LU factorization of this metric yourself. Thank you. This is the end of the first part of the section.